Okay, welcome everybody to the fourth live session. We're going to discuss some questions you guys posted this year or this week. You have a lot of great questions, so we're going to dig right in. The first one was about Gene's golf course assignment. So this one, a student wanted to see what our solutions looked like. So we're going to switch over and go and see, do a little tour of what my solution looked like, and Phil's going to give me a little feedback on what he thinks my code could improve for how it goes. So give us a second, we'll switch over here.
Okay, so we need to pull up what, edX or Bokream?
Yeah, Bokream. Yeah, should be fine. You're going to want to go to, so this is, yeah, that's the submissions part. So we want to go to
here, right here.
This, yeah, the second one. Oh, sorry, actually, no, the first one, but it doesn't matter here. And then go to assignments. And then, yeah, that's the right one. Then genesgreen.py. That's the starter code, so that's the template. There's the real one.
There you go.
Awesome. I can't make that any bigger. Okay. All right. So
Share screen.
let's share screen. Screen 2. Actually, let's just do this. That one. Okay, so this is my solution here. In Bokream. Oops. That doesn't help very much. Can I do that? Awesome. Okay. So I start off with a series of functions. The first one is square yard smooth sod. It takes width as a parameter. Square yard sand takes width as a parameter. Square yards of rough sod. Tons of sand. So this one was smooth sod. Then I got these area of sand, the area of rough sod, which is smooth sod. I calculate, and I take the calculate sand, and then I take the total area, subtract smooth and sand from it. Then I calculate my tons of sand by doing the radius here is 3 times the width over 6. So this take the 3 is for yards. The divided by 6 is the diameter of the sand trap is 1/3 of the width of the area of the overall hole, and then radius is half of that. So I divide by 6 here. Then I calculate the volume by taking that area and multiplying it by 1 foot of depth. Then I seal that. Seal the result of volume times 100 because it's 100 pounds per cubic foot, and I divide by US metric ton, which is 2,000 pounds per, or US standard ton, not metric ton. So this ends up being 2,000. So I get the result for tons of sand there. Number of bricks follows a similar pattern where the circumference of the sand trap area, which is a width divided by 3, times 3 to make it yards, times pi to make it the circumference. So this is the diameter times 3 to make it yards. Then I seal the circumference by 2 because it's only around half of it, and I multiply it by 3 to get my result there. Number of bushes is the perimeter minus 2 because I'm just removing 2 bricks or 2 bushes for the trails that lead in and out of the hole. Then mowing time is my rough area and my smooth area. I calculate those. Then I multiply my rough area by half a second. And then smooth time is 1 second per square yard of smooth area. So I add those two together, and then divide by 60 to get minutes. And that's my result. And then the overall program, the high level program, is I take input for the course length and width, convert those to floats, then just sort of call my functions with some output here to get everything through there. So Phil, what do you think?
It's pretty good. This is not bad at all. I like the fact that you broke this out into a set of pretty small functions. Each one of these functions does a single well-defined task, calculating the square yards of smooth sod, calculating the square yards of sand, and the square yards of rough sod, for example. Each of these functions takes as a parameter the information that it needs in order to compute the result that you want, and then computes the result and returns it. Nice use of the built-in functions in the math standard library. I noticed that when you were describing this line right here, it took you a while to explain what this 6 meant. And that's a little concerning. If it takes you a while to explain why this 6 is here, then that explanation should be in the code in some way, perhaps a set of comments that explain why this is divided by 6, or maybe you could name that 6 by storing in a variable that explains what that value means. The name of the variable would explain what that value means. But you do have plenty of comments in here, and you took care of that same concern here where you have this 2,000 that you're dividing by, but you make a comment saying 2,000 pounds per ton. So that's just the conversion factor. So that's readily apparent. So there's really 2 ways to kind of explain these things in the code. You can put comments in the code, or you can spend some time coming up with some additional variables that are well named, or renaming some of your variables. In general, it's better to have well-named variables and the code describes itself rather than have to have comments that describe the code. Let's see. Again, the comments down here are really good. So they explain what these 2 3s mean. You know, you see this 3 here and you see this 3 here. It's the same number, but it has a different meaning in each of those contexts. You know, this is a conversion factor from yards to feet, and this is how many bricks high the wall is. You could, of course, store that 3 in 2 different variables with that name, but this is a fine solution as well. Another concern I had as you were explaining is in your mowing time function, you have a variable called rough time, which implies that this is going to store a time value, yet you're calling the square yards rough sod function, which returns an area in square yards, and storing that in a variable whose name includes the word time. So that's a little confusing there. So this is really the rough sod square yards, and this is the smooth sod square yards. Is that correct?
Mm-hmm.
And then down here, you're multiplying the square yardage by the actual specified mowing time for that type of grass, whether it's rough or smooth. And again, these numbers are kind of without explicit meaning or context here. So I would spend some time cleaning up the naming of these variables in here and finding a way to make it clear why we're multiplying by 0.5 here and dividing by 60 here. But other than that, it's a very nice program, well organized, nicely broken down, excellent demonstration of the use of functions with arguments and return values, and each function doing a single well-defined task.
Awesome. Thanks, Phil.
Mm-hmm.
Something that I did see in you guys' code that a few people did was they defined functions for for finding the area of a circle and for the circumference of a circle, and those things are used. You can see it right here in my smooth sod and sand ones. I'd use that same function. I have a variable called area, and I perform a math operation twice doing that same thing. So I'm repeating myself, and I might as well say, define myself a function that actually does this, so I could be a little more clear on what is happening in these functions. So that's one improvement that I can see myself making, in addition to the things that Phil mentioned. So that's our example of how Gene's Green worked. I hope that was helpful to you guys. The next question is, what's the difference between a function and a subroutine? Do you want to take that one?
All right, yeah, I'll try this one. So for the most part, in most modern programming languages, and specifically Python, Java, C++, the two terms can be used pretty much interchangeably. The term subroutine is a bit archaic, so you don't tend to see it used as much these days, but they generally have the same meaning in modern settings. Now, in the past and in certain specific areas of computer science, the two terms do have functionally different meanings. And I think you're probably better equipped to illustrate that.
Yeah, so in machine languages, in the languages that the machine runs directly, there are sometimes instructions called go sub or call or things like that. And these refer to the ability for the machine itself to operate as sort of a function call. So it basically what it says is go to this part of the list of instructions, and then there's a special instruction called return sub or recall that goes back to where it was called in the first place. And this takes advantage of special elements of the CPU and special instructions at the very lowest level. And usually this is what we refer to when we talk about subroutines, even though it is functionally a similar process where we're calling something by name and then going and doing it and returning to wherever it was called once it's completed. Things like passing arguments and passing return values back and forth become really complicated at that level because we don't have sort of as much flexibility as these high-level languages does. So this is an example where a high-level language, we call it a function, and in a low-level language, we call it a subroutine, even though they're similar concepts. And this is where we actually get a lot more flexibility using a high-level language by doing it this way rather than having to specify all the little niddly bits at the subroutine level. So if you ever take a computer architecture class or anything like that, that's the kind of thing you might end up being able to do is working with subroutines and machine language. And that's where you kind of see the difference, the real differences between them.
Cool.
Awesome. Question asked was, between Java and Python, is any of them worth pursuing further after the course?
Absolutely, yes. Both of those languages, I think, are worth pursuing after the course. They are both widely used languages across broad spectrum of programming applications in the industry. They're two of the most widely represented languages on the TIOBE index, which is an index that is a measure of the popularity or use of a programming language based on its search history in search engines like Google. I think the others that round out the top of that list are C and C++ and C#. And that would be the top 5. Is that right?
Yeah, that's correct. So the top 4 are Java, followed by C, followed by C++, followed by C#, and then Python is number 5, but it's rising. So we see a lot of these in this particular index. Even it's saying that over the last month, Java has slipped 5%. Right now, that doesn't mean that necessarily Java is losing popularity, or in the future it's not going to be useful to know Java. Java is still, to give you a comparison, 12% of all code written, as TIOBE thinks, is written in Java, right? So that's an awful lot of code per year written in Java. The next one down is C, and this is usually what embedded systems are written in. So if you're dealing directly with hardware, which is a lot of the Internet of Things stuff, or writing operating systems or anything like that, that one is at 7%. So Java still has 5 or 6% over the next biggest language in the world. What's really happening here is that more languages are coming to the party. So more languages are becoming popular in all of these different areas. And this is exactly why we chose Python and Java for this class, because Python is an up-and-coming language. It's risen massively. It wasn't even on the list in 2 years ago. Now it's number 5. So it's rising very quickly. Lots of new development is happening, and there's lots of specialty languages that are being developed that are now coming into popularity for all kinds of different applications. So these two languages are a good balance of the different kinds of languages you'll see out in the world, and we think that both of them are great opportunities to pursue new development and new learning wherever you go.
Right. And to put a little bit of historical context on that, Python is absolutely the newcomer to this list. It started becoming a known language used by small communities in the late 90s. C, on the other hand, goes back to the 1960s, C++ to the early 90s, C# and Java soon after that. So the longevity of these languages is still probably decades. And these are some of the more popular languages that have a critical mass of users and a dynamic, evolving language that is continuing to grow and adopt new characteristics and features as the needs of its users change over time. So I don't anticipate any of these top 5 languages being a waste of your time.
Yeah, absolutely. So the next question, actually the next 2 questions are sort of related. And the first one is, what other courses should I look for in the MOOC world if I want to continue learning how to be a computer scientist and to be employable as a computer scientist? And then relatedly, are there other important subjects that I should learn in order to advance and start a career in computer science? So my view on this is kind of a, let's call it a top-down sort of approach. And the idea for me is that you kind of want to think about where you want to be. So there's lots of different kinds of computer scientists out there. You could be working in medicine and bioinformatics. You could be working in software engineering for a large company like Google or Amazon, or you could go and develop web apps, or you could develop apps for your phone, or develop hardware, or anything like that. So there's lots of different opportunities for people that know how to program. Look at one. For this individual, for all of you out there, what I would recommend if you're interested in pursuing a career is look at these different jobs and see what looks interesting to you, what looks like it would be fun, and then start looking at the job postings for those. Not to necessarily apply for them now, but it'll give you an idea what they're looking for in terms of skills right now. And that'll give you a target that you can hit. And you kind of build a ladder of skills that you need to meet in order to be qualified for a job like that. And it may seem insurmountable, but it's really not. There's a lot of opportunities, and there's a lot of resources out there, classes like this and more advanced classes like this, where you can sort of see what you need to do. So they might say something like algorithm development and analysis or something like that. And that might be a higher level course on algorithms and data structures. And then what do you need to do to get into that sort of class, and what kind of skills do you need to develop and stuff like that. So kind of work from your target back to what you need to do next.
Right. No, that's good. Another thing you might look for if you're specifically looking for courses is in the schema of a computer science degree. A course like this one is what's called a CS1 course, or a freshman CS course. So you'd be looking for, as a follow-up to this, a CS2 course, or a junior, not a junior, a sophomore level CS course. And then looking for a course that says something like object-oriented programming, or data structures and algorithms, or analysis in the course title, is going to give you a clue that it's a next level up. But short of courses, there are a lot of additional resources, and you touched this. There are a lot of good online tutorials that I think this course will prepare you to be able to engage. Some of those tutorials are a little difficult for someone with no experience to kind of dive into and sort of learn on your own. But I think once you complete this course, a lot of those online tutorials are going to be perfectly good resources for you. And then I'm a big fan of books. I've got books on my shelf here. I've got books everywhere. And I recommend going to a library or a bookstore and just perusing the CS section and pulling some books off the shelf that look interesting to you. I would recommend finding one book that's tutorial style. And such a book would basically be explaining some concepts with some little things for you to try along the way, and then explain a new concept. It's very much like this course. And then maybe a reference book if you're going to focus on Java, or you're going to focus on Python or C or C++, a reference book that you can quickly and easily look up some aspect or feature of that language while you're going through the tutorial book. So those are some good next steps, I think.
Yeah, absolutely. And some of the sort of peripheral skills that go along with being a good programmer or a good computer scientist or software developer is being able to follow the software development process. So there's a lot of ways to do this. One of the more common ways is called Agile programming, and a lot of companies use this. Look into how that works and what that can do. There's lots of classes on Agile. If you have that on your resume, companies will be very excited to talk to you, stuff like that, once you develop your skills. And on the flip side, there's no substitute for practice, right? So to really develop your skills, it's not just about going through classes and sort of tinkering or looking at books and stuff like that, but it's that tinkering part and expanding that to doing some projects for yourself, right? One thing that I just did and I learned a ton about is I run a capstone program, and the companies that I work with to submit proposals, they send me all kinds of documentation on the projects they'd like to do and stuff like that. And me gathering them and putting them in a form that my students can read and all kinds of stuff like that takes forever. It's literally taken me like several days of work just to put together this one big document. The other day I wrote a script that automates the whole process. So they submit everything online, I run the script, it compiles it all into a Word document, and I can print it as a PDF and hand it out to my students. And that's going to save me so much work, and I learned a ton doing it. Phil is reviewing my code, and he's giving me feedback. I'm learning a bunch about it. And so this kind of stuff is happening all the time. And if you can do projects like that make your life better and sort of stretch your skills, that's a great way to learn. And stuff like that is great to talk about if you're doing interviews and just showing people how much you know and that you're qualified to do this sort of thing.
Cool. That's good advice.
The next question is about the proctoring for the exam. They wanted to know if we're allowed to have any small items during the test. I just heard back from this. We have some requirements that it's only things that are allowed, and Phil and I define what is allowed. We haven't done that yet, but we're going to have a conversation very soon, probably immediately following this webcast, and we will post some guidelines about what you're allowed to have like on your desk during the proctored exam. So be watching for that. We'll put an announcement in the shell in edX that will detail everything that you need to know about what you can and can't have during the proctored exam if you're doing proctored. Oh, this is a good one. I was hoping you might discuss the book sorting challenge. So this was in at the end of dual decisions. There was a knowledge check on sorting different books, right? So we gave you a book sort function that was broken, and we wanted you to fix it. And Phil and I had a really long conversation yesterday about doing this because we were trying to find all of the different ways you can actually solve this problem, right? That's the new one. So what we did is we're going to look at the solution that Wendy posted, and then we'll talk about some of our solutions here, right? So it'll be, yeah, go there first. And all discussions, it should be number 1. And then her solution is down here. There it is. Awesome.
So let's see.
Sure. Okay. Okay, so this is Wendy's solution, and it's a totally solid solution. This was this is an improvement on sort of the exhaustive version of this one. So in the example, I only gave you 3 cases, right? So there was one where the first title comes first, second title comes second, third title comes third. Then there was a case where the first title comes first, then the third, then the second, then the second, then the third, then the first. So these cases are incomplete. There is actually 6 possible combinations of orderings of the books, and I only gave you 3. So you could exhaustively say if the first one comes first, if the second one comes second, if the third one comes third, then do first, second, third. If the second one comes first, then the third one comes second, then the first one comes last, then print them in that order, and so on and so forth. So you could do 6 different cases, and it would be pretty long, right? Totally valid solution. What Wendy did is she said, let's first detect what title should go first, then decide which title should go second and third. And she did that for each of the 3 cases. So we end up with 6 smaller cases and a partial first case at the very beginning, which I think is cool. This looks really good to me. It's really readable. And it's a pretty concise one. And Wendy, I like that your instinct is to feel like this is a little clunky or a little chunky. That is a great instinct to have. And trying to fight that instinct will make you a better programmer, because you're gonna push away from things that are big and long and awkward, and that's great. One little tiny detail in your code is that in the second elif, the nested elifs, those could be else's. You don't really need the condition there, because if it gets to the first part and it doesn't pass that second one, we should always do that little bit there, right? So that makes sure if you just do an else, you don't have to have the condition, and it drops right down into it, and it's totally correct. That's the only thing that I would comment on improving your code. Now, Phil, you've come up with a couple of examples that we can look at for alternative ways to solve this problem.
All right, let me pull those up. I'll just pull this screen up over here. So this is just a couple of different examples, and these kind of came out of our discussions yesterday. So we discussed that what we would like to do is to sort this. And most programming languages and standard libraries have built-in sorting algorithms, because it's a pretty common thing to do. We haven't showed you how to use those, so there's no expectation that you would use those. And we did want you to code this by hand. But one of our ideas was to, by hand, code one of those sorts. The simplest sorting algorithm is what's called a bubble sort. And then this first example here demonstrates that. So we've got these 3 items that we want to output in order. And so the first thing we're going to do is check to see if B should come before A. Then we're going to swap A and B. We do that by temporarily storing A in temp. Then we can store B in A, and then we can store what was in A and B. And so this is just a simple 3 lines of code that swap the values of A and B. And then we can compare A and C. And by the time we're done with this second comparison and possible swap, we're guaranteed to have the smallest value stored in A. And then the last thing we have to do is compare B and C to find out where the second and third values should go. And by the time we get here, the smallest value should be in A, the middle value should be in B, and the largest value should be in C. So, and then we talked about the exhaustive approach. So this is just asking each of the 6 possible questions. If A is less than B and B is less than C, then the order is A, B, C. Else if A is less than C and C is less than B, then it's A, C in the middle, B. And else if, and this might seem a bit tedious and redundant, but it's a totally valid way to solve a problem like this, is to account for every possibility. It's nice to be able to identify efficiencies and simplifications in the code, but in reality, I don't find this code to be particularly complex. The most complex part is these string concatenations in the print statements. The compound conditions, if A is less than B and B is less than C, to me it's pretty readable and sensible. And then when Ryan and I were talking about this yesterday, Ryan came up with what I think is a very interesting solution using Python's built-in min function and max function. Ryan was saying that the first thing he would want to know in solving this problem is what comes first. And the min function can tell us that. And so using the min function to figure out which of these three comes first, and then the max function to figure out which of these three comes last, and then what remains is to figure out what goes in the middle, and what goes in the middle is the one that's not the first and is not the last. So if A isn't the first and A isn't the last, then A is the middle. Else if B isn't the first and B isn't the last, then B is the middle. Otherwise, by process of elimination, C is the middle, and then we can just output the first, the middle, and the last. And it's worth noting here that these three examples plus Wendy's example are just four of a very large number of very different possibilities, all with advantages and disadvantages, strengths and weaknesses. And this is one of the things that I really love about being a computer scientist, about being a programmer, is this creative aspect. The fact that I can make my solution to this problem, and as long as I can justify the choices I made, that's a good solution to the problem. You know, and Ryan can make his solution to the problem, and as long as he can justify the choices he made, that's another good solution to the problem. And, you know, we may disagree on the basis of those decisions, but we can agree that, you know, if that's the basis of your decision, then this is a good solution. And I like that creative aspect. The fact it's a lot like creative writing to me. A lot of different ways to solve this problem. So it's not like a math where I feel like most math problems, there's like one right way to get the one right answer.
Right. Totally. Awesome. So the next question is, this person would like to know when a return is required as part of a function as opposed to just an instruction that executes the print function.
Okay.
Yeah. So my instinct here is that print is for a specific purpose, right? Print is for output to the user, right? Return is for exchanging data between different parts of your program, right? If you want a function to evaluate to something, use a return. You have to use a return. That's the only way it actually works. Print only gives it to the user. That's not information you can actually use elsewhere in your program. So if you're ever going to use that information again, put it in a variable using a return, something like that, right? The other thing might be to consider, what do you think, like the division between output and processing?
In what way?
Like a function should do a thing, and then that one thing is it.
Right. And we sort of ask you to violate some of these rules for the purposes of little assignments, because we'd like you to write a small piece of code. But there's a good argument for saying that concerns like input and processing and output should be managed separately in your code. And a function should perform a single well-defined task. So if you have a function that's supposed to calculate some value, maybe it's the total area of rough sod, then it shouldn't both calculate the total area of rough sod and display the total area of rough sod, because those are two different things. And you could ask yourself this question: is it possible that I would ever want to calculate the area of rough sod but not display it? And if the answer to that question can be reasonably yes, then you shouldn't put that display functionality in that function. You should have the function return a value, which another function can then display.
Yeah.
So that's a very good point.
Absolutely.
Another way to kind of look at some of this, there's a relationship to the concept of arguments or parameters here as well. So when the kinds of programs that we're writing in this class right now are what are called procedural programs. They're programs that are made out of functions. Ideally, each function performs a single well-defined task, but the functions have to collaborate. They have to work together in order to realize all the functionality that we need for the program. And this requires communication between the functions. Sometimes we need to tell a function something in order for it to do what we want it to do. So if we want this function to calculate the total area of rough sod, we might need to give it the width of the golf hole or the golf course. And we would do that by passing an argument into its parameter variable. So that function would have a parameter if that function needs to receive some information. And sometimes we need information back from a function. And when a function is going to give information back, that function is going to do that with the return value. So sometimes we have functions that don't need to take any information and don't need to return any information. They're not going to have parameters, and they're not going to have a return value. Sometimes we pass information and it has parameters and no return value. Sometimes it just returns a value and we don't have to pass it anything. And sometimes we need two-way communication between, whatever we're calling the function from and the function itself. So we can pass some things in as an argument and get a return value back. And we use the arguments or parameters as we need. If the function needs to be able to receive some message when we call it, then we're going to use parameters or arguments. And if we need something back from the function, then we're going to use a return value.
Yeah. So relatedly, we have a question from James online, and he's asking about if you can change global variables from within a function, and also what about returning more than one value?
Okay, so the big answer to those questions is yes, we can do both of those things. We're not going to focus on that in this course, but those are reasonable things that you might want to do. They add a degree of complexity to the code. If you are going to continue your study and exploration of these concepts, and specifically the Python language after this course, you'll encounter how to accomplish these things very quickly. It's not particularly difficult, but we want to focus on a very specific set of core concepts related to computer science in this course, and so we're kind of pushing that aside.
Yeah, totally. So, James, this is you mentioned this in reference to Perl's Pancake Pad and how we're handling the totals for the day. So the idea is that the wait staff can enter the bills for each of the diners at a table, and then once that's exited, all of the individual bills for the once the orders are taken, all of the individual bills are printed out. Then you do that several times for different tables, and the whole time you're accumulating how much money should be in the register at the end of the day, how much money is in the register at the end of the day. And this includes the ticket totals and the tax for the entire day. And I think what this gets to is that you should, you probably will have a global for that register total at the end of the day, but you really shouldn't. You should try to avoid modifying it from within the function, because that's really only one number, right? So maybe you should have a function that deals with one order and it returns that, or one table, and it returns that total for that one table that you can just add to the global function outside of the add to the global variable outside of the function. One breakdown, we consider it a flaw in your program if you are using globals inside of functions, right? So things like constants that are defined globally, constants that should never change, like pi and conversion ratios, those are probably okay. But the things that are variables, things that will change over time, if you're using those and trying to access them from inside your function, that's a problem, right? And that means you're not structuring your code appropriately. That's what we call a code smell. It means that it's smelly if it doesn't if it breaks one of these types of rules. And globals, accessing globals from within a function means that you're either not providing the function with what it needs through the parameters, or you're not returning values that you should be pushing out to the outside world. So that's kind of the take home for that one.
Yeah, it tends to make the programs, especially as they become even slightly more complex, much more difficult to test and to debug and to maintain.
Yeah. The next question is, how do we know when to put an if statement or else if ladder inside of a function as opposed to just making it part of the code?
Okay, so I think, so we're talking about should an if structure go inside of a function, or should it be at the program level? First thing I'm thinking in an attempt to answer that question is an if structure should go inside of a function if that function needs to make a decision as part of what that function does.
Mm-hmm.
You know, so maybe this function is going to determine whether or not this customer gets a teddy bear. You know, so the function is going to return a Boolean value. It might need to make a decision as to whether it returns true or false. That decision might be based on some condition that includes the total purchase amount that customer is making. In that case, I would say that function needs to make a decision as a part of what it's doing. That function would have an if structure inside of it.
Yeah, yeah. So the decision is really about how you're breaking down the functionality in your program, right? If you have a unit that needs to do this thing, and part of accomplishing that task is making a decision, then that decision should definitely go in that function. If it's a higher level thing, you can do that, but kind of think of it as, what if I had a function to do this? I'll put an if statement inside that function, right? You should always try to break it up into these little units, little units of functionality inside of functions, and if you can do that, and you need to put an if statement in there, do it, because it makes your code clearer and it makes everything structured a little bit nicer. So I think we had one last sort of related question to a discussion we were having earlier from the chat room. How many hours would you recommend to practice and improve your skills? Yes.
I think that's going to differ on your personal motivation and your personal needs. What is it that you intend to achieve? What are your goals? And how quickly do you want to meet those goals? How much time do you have to apply to this? So I know I can become pretty absorbed in studying some of these aspects and lose hours without realizing that time is passing. So I would say, general rule of thumb, I would say is, spend as much time as you have available and enjoy spending doing this.
Yeah.
Don't sacrifice other important things in your life that need to be done.
Yeah.
And if you really don't enjoy this, I'm not sure it's worth forcing yourself to do it. So.
Yeah. And I know when I started programming in college, this is really weird because I learned some basic programming when I was a kid, and I learned a weird version of C when I was in high school. And then when I got to college, I was learning C and C++, and I hated it. I was just banging my head against the wall. I was not having any fun. But a year later, I joined the robotics club, and I was using the same stuff that I learned in class. And it was because I had a place where I could put it. I wasn't just like doing math problems for the sake of, a grade. I was doing it because this is awesome, right? I had a robot. It was running around on my table. It was doing some cool stuff, and it was something that I built, right? So the context in which you do things really helps figure out what your passions are and where those sorts of things lie. So if you're having fun, if you find something that's interesting, you're going to have a lot more fun doing it, and it's going to take as much time as you are able to give it to sort of improve yourself. So if you're having fun, keep doing it. That's the key part there, and that's kind of what I end up doing when I'm trying to learn a new skill or anything like that. Is when it's not any fun anymore, it gets way harder to dedicate that time to it. And so often I'll stop early, take a break from something, and then come back to it later just so it stays being fun rather than being a chore or being something like that. That said, if you're working toward a specific goal on a timeline, things change there, because that's the price of fun in the future if you're making that investment. So it's really up to you in your particular situation as to how you handle how much practice you put into something.
You talking about your personal experience where when you started doing robotics and applying it to this thing that you enjoyed, that worked really well for you. That circles back to some advice you gave him a little earlier in this session, which was, find areas where you can apply this in your own life. Find something that you're already doing, and preferably, either something that you would rather have automated, because you can write software to automate this for you, or maybe it's something you really enjoy doing. So I'll give an example myself as well. One of my favorite things to do to kind of pass time and relax is I like to find books and websites that offer puzzles, mathematical puzzles, logic puzzles, very challenging puzzles. But rather than doing them by hand, I like to craft computer programs that solve the problem for me. So one thing that my wife and I do is every Sunday we listen to the NPR Sunday Puzzle, and then they give the challenge for the week. She immediately sits down with pencil and paper and tries to solve it. I immediately run into the office and try to code up a solution, and we see who can get the answer the fastest. And so far, I think she's probably a little better than me, but I enjoy my process.
Yeah, that's awesome. Okay, so that's the end of our the submitted questions and the questions online so far. We've got another about 10 minutes left, and what we'd like to do here is talk a little bit about the midterm that's coming up next week. This opens on Monday, so to help you prepare for it, we've got a couple of resources. The first one is there's a study guide online. If you go to the top bar on the class, it says midterm and final exam study guides. That basically gives an overview of all the topics that we're going to expect you to know in order to prepare for the exam. So these are places where you should go and read and rehash those topics and make sure that you know what it is that you're preparing for. One approach that you could take is to go back through the course page by page, unit by unit, up to where we are now in structured programming, and take notes, right? So just the act of reviewing it and writing down what you think is important is going to be a huge boon for absorbing this material and refreshing it in your mind before the exam. That is what I would do if I were studying for the exam. Phil, do you have another tool that I can use?
I mean, I think those are good. I think it's worth, a number of the questions on the exam are going to ask you to read, interpret, and evaluate source code examples. So one of the things you might do is go through, as you go through the course and you run into source code examples there, pull those examples out and try to work them by hand. So you play the part of the computer and keep track of the variables and the current values of those variables and which instruction is executing next and what effect does this have on the value of the variables when this instruction executes, and work your way through that. So do we have time to show a couple of these?
Yeah, we got
Okay.
10 minutes. While Phil is switching over here, I'm going to mention what the exam is made of. So we have the midterm. It has two pieces. There's a multiple choice section, which is about 60 questions. I think it's 61 specifically. And these are multiple choice, true, false style questions. Now, that doesn't mean these aren't code questions. These, what we might do is give you a piece of code and have you, say, interpret it and ask you what the output will be or what the value of a given variable will be, or something like that once the code is executed. So those are 60 of those. And then followed by 8 small programming problems. So there's going to be 2 parts. There's going to be the sort of typical multiple choice exam questions part, and then there's going to be a vocarium part where you're going to write tiny functions. Mostly all of them are functions or statements, and they're to accomplish some very specific tasks. So, and those are all auto-graded as well. So it's very common. In all of the small programming problems ones, you shouldn't be asking for input. That'll break the exam. That's a big no-no there, right? So just write the function, just write the expression. All the tests will be performed on your code there. Don't ask for input from the user. So that's the summary of what you should expect. You're also going to have 4 hours to complete the midterm exam. That doesn't mean that it's going to take 4 hours to complete the midterm exam. We're just trying to give you enough time that everybody that starts it can finish it, right? Even if you have to take a break, or well, actually you can't take a break. It has to be all in one sitting. If you're doing it for credit for proctoring, you have to prepare to sit for the entire part of the exam, because if you leave the room or go to the bathroom or anything like that, that ends the proctoring session, and that's as far as you can go, right? So it's really important that you're prepared to do the exam all in one sitting as you go through this part. But again, it doesn't mean it's going to take 4 hours. It just means that we're trying to give you all the time you need to finish the exam in a reasonable amount of time.
And it is designed to be a robust exam. It is designed to be as much a test of how well this course is doing at helping you learn these concepts as it is a test of how well you're learning these concepts. And so I would say don't be intimidated by anything on this test. Don't leave anything blank. Hit every question with the best answer you have. And there's 4 hours there, and if you want to take those 4 hours, take those 4 hours. We don't want you to feel rushed in this exam, which is why the 4 hours is there. But yeah, it probably wouldn't take anybody 4 hours if they were really trying to do this in a shorter amount of time.
Yeah.
So I have a couple examples of some of the questions that I think you might see on the exam, and some advice on how you might go about attacking them. And I think we're going to try to make it possible for you to have some blank scratch paper and a pencil or a pen with you, so you can do this kind of thing. But you'll find some questions on the exam like this one that ask you to evaluate this code and determine what's going to be outputted. So what you're going to want to do in a situation like this, when you're asked to evaluate a set of code, is if there's variables involved, you're going to want to keep track of the values of those variables. So I'm just going to list the variables over here. So I've got an A and a B. Those are my only variables. And then I'm going to start playing the part of the computer, and I'm going to say, well, if we execute this line of code, then that's going to store a 3 in A. And then we'll go on to execute this next line of code, which is going to evaluate the expression A plus 2. A is 3. Plus 2 is 5. That's going to be stored in B, so we're storing 5 in B. And then this statement is executed, and we're going to evaluate this expression, A minus 1. 3 minus 1 is 2. Gets stored in A. And then we're going to execute this instruction, and it's going to print the value of B. So it would print the value 5. The output would be 5. Mm-hmm. Similar example down here, we have a variable A, B, and C. So I would just write those down. And then as these lines of code are executed, what effect does that have on the values of the variables? Store 3 in A, store 2 in B, evaluate A plus B, that's 5, store that in C, store 10 in A, output the value of C. So again, it outputs 5. So, and if these feel simple, that's great. They hopefully should. This is some stuff we learned very early on in the course. Some of the questions are going to be a little more challenging. So here we have a small program composed of 3 function definitions, and then we call one of those functions. And in this case, it wants to know, the question will want to know, well, what will the output be? So we have a series of print statements here. So we're going to need to determine which of these print statements are going to execute and in what order. So when the ZAM function is called, the first instruction in there prints ZAM. So that's the first thing that will be outputted. And then bar function gets called from here. So we enter the bar function. This calls the foo function, which prints a foo. And then the foo function returns to where it was called from, and we continue where we left off, and we print a bar. And then we call the foo function again, which prints another foo. Foo function returns to here. The bar function returns to here. And we return from this call, and we're done. So this outputs, when we run this little program, it outputs zam, foo, bar, foo, which is weird, but it's just a way to kind of assess, do we understand how sequence works and how functions calls work, and when functions call other functions, how that works.
Yeah. Now, if I were doing this on paper, I would have some marking. So we have this built up in our minds of where our function is called from and where it's going to return to and where we currently are executing in this. So when Phil was doing this, he started with print zam, then he did bar. And in his mind, he was marking and saying, this bar line is where I'm going to return to from the end of the bar function. Then he calls, inside the bar function, he calls foo. Foo returns to here. Then he prints bar. Then he calls foo again, right? So in his mind, he had marked that this one is where the foo returns to. Then he calls foo again. Foo returns here. At the same time, this is still all in the bar call. So when the bar comes back, it returns back here. So I would have probably some arrows or something drawn around to remind myself and help me keep track of where these things are on when I'm going to return back to them, if I've executed them already on this particular call, stuff like that.
Cool. We'll have some examples where the functions take arguments. So let's take a look at it. And in this case, if the functions take arguments and the functions have local variables, then we're going to need to keep track of the local variables memory separate from the global variable memory. So remember, any variable that's assigned inside of a function, including parameter variables to the function, are local variables. So this function has a local variable called x, and this function has a local variable called x. And then in the global scope, we have a variable called x. So in this code, when this code runs, we've got 3 different variables called x. They're not all being used at the same time, but potentially. And so when this runs, the first thing that happens is 5 is stored in the global x. And then we call foo, and we're passing x. And remember, when you pass a variable, we're really passing the value of that variable. So the value of that variable is 5. We're passing 5 to foo. So its x parameter is being initialized with the value 5. And then we can execute its first instruction, x plus 2. Always look local first. So this local x is 5 plus 2 is 7, gets stored in x. And then we're going to print that. So that's going to print 7. And then this function is finished, so it's going to return to where it was called from. And we pick up where we left off, and we're going to call the bar function, and we're passing x again. So remember, here we're in the global scope, so we would be using 5 again. Again, we're passing 5, in this case to bar, initializing its parameter to 5. And then the body of this function can execute. It evaluates x plus 1. Always look local first. We find a local variable called x, whose value is 5, plus 1 is 6. We store that in x. And then we print that. And then this function returns to where it was called from. And we execute the next instruction. And this is going to print the value of x. In this case, we're in the global scope. The value of x is 5. And it prints 5. So this would output 7, 6, 5. And you might put together some little programs like this for yourself, or look for some programs that look like this in the course. And then do this kind of what we call hand tracing or desk tracing of a program, and then put this into a Python REPL or a Runestone component and test it to make sure that it actually produces the result that you anticipated. There'll be some, did you have something?
No.
Okay, there'll be some questions that ask you to evaluate loops. So again, it's just a matter of following the same basic process that you follow up here. You're going to want to keep track of all the variables. Here we have an X variable and a Y variable. Those are only variables. And then when these instructions execute, we're going to store 3 in X. Then we're going to store 1 in Y. And then we're going to test this condition, X less than or equal to 8. That's true. So we're going to execute the body. Y equals Y plus 1. So Y is now 2. X equals X plus Y. So X plus Y, 3 plus 2 is 5, gets stored in X. Whenever we hit the bottom of a while loop, we go back up and we test the condition again. X less than or equal to 8. Yes. So back into the loop we go. Y plus equals 1. Y is now 3. X plus equals Y. 5 plus 3 is 8. It's stored in X. We hit the bottom of the loop. We test the condition again. X less than or equal to 8. Yes, it is. Then back into the loop we go. Y plus equals 1. X plus equals Y. 8 plus 4 is 12. Bottom of the loop. Back up and test the condition. X less than or equal to 8. Nope. And so we skip the body of the loop. We're out of the loop. We print the value of X. X is 12. The answer would be 12 in this case. There'll be some questions that ask you to evaluate decision logic structures. Same process. So we've got variables X, Y, and Z. When we follow these instructions, first we assign 3 to X, then 5 to Y, then 7 to Z, and then we start testing these conditions. Is X greater than Y? No. Then we go to the elif. Is Y greater than Z? Is Y less than Z? Yes. Then we print Y. The value of Y is 5. And once you've executed one body of an else if ladder, you're done. So that's the only output for this. Probably the most complicated thing would be something where you're looking at code that maybe has a loop with a decision nested inside of it, or a decision with a loop nested inside of it. So we'll do one example of that, and then we'll move on. So we have variables X, A, and C in this case. So when this code executes, 8 gets stored in X, 5 gets stored in A, 1 gets stored in C, and then we start this loop. We test the condition. Is X greater than 1? Yes. Then into the loop we go. The first statement in here is a decision. Is A greater than or equal to X? No. Then we do the else. So we're going to assign to X A minus 2. 5 minus 2 is 3. That gets stored in X. That's the end of that decision structure. And now we're going to store in A minus 2. So 5 minus 2 is 3. Store that in A. We're going to add 1 to C. C is 2. This is the bottom of the loop. So we go back up and test this condition again. Is X greater than 0? Yes. Then into the loop we go. Is A greater than or equal to X? It is. It's equal to. So we're going to execute this instruction. We're going to evaluate A plus 2. 3 plus 2 is 5. And store that in X. And since we executed this, we skip the else. That's the end of that condition. We're down here. We're going to store in A minus 2. A minus 2. 3 minus 2 is 1. We're storing that in A. We're going to add 1 to C. C is 3. Bottom of the loop takes us back to the top and tests the condition. Is X greater than 0? Yes. Into the loop we go. Is A greater than or equal to X? No. Then we're going to execute the else. We're going to evaluate a minus 2. So 1 minus 2 is -1. And we're going to store that in x. And then we're out of the decision. We're going to evaluate a minus 2. A minus 2 is -1. And we store that in a. We're going to add 1 to c. C is now 4. We go back up. We test the condition of the loop. Is x greater than 0? Nope. Then out of the loop we go, and we print c, which is 4.
Awesome. So these are great exercises that you guys should try yourself as you go through. Jill made a great note that that if you leave during the proctored exam, that can be construed as cheating. So make sure that you've gone to the bathroom and you've had a snack and everything before you start the exam, just so that you get all the credit that's due to you, and you can get through it without having any trouble. Again, it sounds like a lot, but the exam questions, if you're well prepared, should sound easy. They're not going to be. We're not here to trick you or anything like that. A pencil and paper is going to be handy, and we'll have a clarification posted on exactly what is allowed during the exam probably today. So thank you, everybody, for everything, all the great questions. Keep up the good work, and we'll see you in the discussion boards.